It's a very, very hot summer day. You can barely breathe, it's that hot. And the humidity makes it even worse. You have a ton of things to do outside, you somehow manage to get them done, and then you throw yourself into your air-conditioned home. You go to the fridge and grab an ice-cold drink. You enjoy the watermelon you sliced the night before, now perfectly chilled. It's a strange kind of happiness, and billions of people throughout history never experienced this feeling. Those of us who can are truly privileged. Air conditioning and refrigeration, inventions that fundamentally changed civilization, indispensable parts of our daily lives. But do you know what lies behind these inventions? Behind this comfort are centuries of physics research work that, starting in the 18th century, carried civilization to where it is today, dramatically shaping the food industry, all branches of manufacturing, urbanization, and life itself. More specifically, it is humanity's battle against heat and cold, a battle of meaning, a struggle to dominate cold and heat, one that includes countless mistakes, absolute zero, thermodynamics, and the groundbreaking theories, experiments, and ideas of names like Sadi Carnot, Kelvin, Fahrenheit, Joule, and finally, someone we've talked about before and who, in my opinion, easily competes for the top spot among the greatest scientists in history, Michael Faraday, a battle that we ultimately won. Welcome to the story of humanity mastering cold. Cold. For hundreds of thousands of years, it was associated with death and darkness, seen as a malevolent force. Was it an unexplained substance? A thing that existed on its own? It was actually a very important question, one we didn't think about nearly enough. By the 17th century, during the period known as the Little Ice Age, when extreme cold gripped much of the world, this question deeply troubled people once again. One of the figures who dared to tackle it was one of the most important alchemists of the era, Cornelius Drebbel. In 1620, before King James I, Drebbel managed to cool an entire church by blowing air over barrels filled with ice, using a hand-powered fan of his own design. In effect, he invented the first air conditioner in history. But truly mastering cold required something that, at the time, was still poorly developed: the scientific method. From this perspective, another name obsessed with the question, what is cold, would step in about 50 years later: Robert Boyle. Born into a wealthy family, Boyle spent his fortune building what was essentially a private laboratory. He began with experiments on the nature of air, but soon became one of the first people to seriously investigate cold itself. Does cold come from the air? Is cold simply the absence of light? Are there particles that produce cold? Alongside these questions, Boyle conducted a very simple experiment. One evening, he carefully weighed a barrel of water. He then left it outside overnight in snowy weather. As we know, when water freezes, it expands and can even break its container. If cold were a substance, perhaps this would prove it. But when Boyle weighed the barrel again the next morning, he saw that its weight was exactly the same. From this, Boyle drew a crucial conclusion. Cold was not a substance. Nothing had entered the barrel from the outside. Instead, the particles that made up the water had simply moved farther apart as they cooled. According to Boyle, heat was related to the motion of matter, and as matter cooled, that motion decreased. And remember, he reached this conclusion in the 1600s. With the tools of that era, this was an extraordinary insight. To understand just how difficult this was, consider this. What would have helped Boyle the most while studying heat and cold? A thermometer. And he didn't have one. Thermometers would only begin to be developed around that same time. First, Gabriel Daniel Fahrenheit and later Anders Celsius created temperature scales based on universal reference points like ice and the human body. Both scales are still used around the world today. But while developing these units, both scientists were troubled by a profound question. How cold can cold actually get? Is there a lower limit? Could there be something like an absolute zero? Yes, there could.
Even asking this question would begin to shift the foundations of physics. Enter the French physicist Guillaume Amontons. Amontons studied how air expanded and contracted when heated and cooled. He placed air inside a glass tube and heated it in hot water, causing the air to expand and push mercury upward. He then did the opposite, cooling the air, and observed that as temperature dropped, pressure dropped as well. And he asked the key question, how far does this go? He didn't have the equipment to test it directly, but he made a simple extrapolation. By plotting pressure against temperature and extending the line, he found the point where pressure would reach zero. And do you know what he discovered? Absolute zero. Minus 273 degrees Celsius. Amontons had theoretically discovered absolute zero. Of course, science doesn't progress only through successes. Even the most respected figures made serious mistakes. One such figure was Antoine Lavoisier. Despite being a giant in the history of chemistry, Lavoisier misunderstood heat. In his caloric theory, he proposed that heat and cold were caused by a weightless substance called caloric that flowed into or out of matter. He even added caloric to the list of known elements, alongside oxygen and hydrogen. This theory was accepted for a long time, but now comes the strange part of the story. A bit of scientific gossip. Last week in our video on the law of conservation of energy, we talked about Count Rumford, also known as Benjamin Thompson. While boring cannon barrels, Rumford discovered that heat was related to motion, effectively ending the debate and dismantling Lavoisier's theory. And then something unexpected happened. Completely unrelated to this debate, Lavoisier was sentenced to death during the French Revolution for tax evasion and illegal tobacco trading. He was executed by guillotine. Afterwards, Madame Lavoisier left France. She later met Count Rumford, the very man who had disproven her late husband's theory, fell in love with him, and married him. Apparently, she had a weakness for intelligent men. To be fair, she herself was exceptionally intelligent and played a major role in assisting her husband's experiments. She and Rumford eventually separated as well. Anyway, thanks to Rumford, it was finally accepted that heat is related to the motion of particles, what we now call atoms. As temperature increases, these particles move faster. As it decreases, they slow down. Rumford would go on to found the Royal Institution of London, still one of the most important scientific centers in the world. These connections genuinely excite me, because now look who steps onto the stage, the father of electricity, the self-taught genius, Michael Faraday. In a sense, he was also the father of cold. While working as an assistant at the Royal Institution, Faraday was assigned dangerous experiments. One involved studying chlorine using chlorine hydrate crystals. He placed chlorine hydrate at one end of a sealed glass tube and immersed at that end in hot water. Soon, yellow chlorine gas formed and increased the pressure inside the tube. At the other end, Faraday noticed an oily substance accumulating. When he tried to break the glass to examine it, the built-up pressure caused the tube to shatter, slightly injuring him. But in that moment, he noticed something extraordinary. The oily substance vanished instantly, accompanied by an intense chlorine smell. Faraday soon realized what had happened. The pressure had liquefied the gas, and when the tube broke, the liquid rapidly evaporated. This phase change absorbed heat from the surrounding air, cooling everything nearby. For the first time, Michael Faraday had artificially produced cold. He repeated the experiment with ammonia, which absorbed even more heat. And do you know what this is? Despite technological improvements and modern systems, this is essentially how refrigerators and freezers work today, a cooling cycle based on substances like ammonia. A system rooted in Faraday's experiments from the early 1800s. So the next time you grab a cold drink from your fridge, you know who to thank. But the story was only beginning. Refrigerators entering our homes were just the visible part. These discoveries would later lead to air conditioning and, more importantly for science lovers like us, to the development of thermodynamics and eventually to the work of Einstein, Bose, and quantum mechanics itself. In other words, we've opened a new front in our quantum physics journey, and we'll connect it to everything we've discussed before to strengthen the foundation, because everything is connected. And these connections show us the whole picture. They answer, once again, the question, what use is this knowledge to us? They show us why we should talk about science, why philosophy of science, theories, strange questions, and seemingly pointless experiments matter so deeply. Our story continues, friends, and it will continue for a long time. We've made a strong return to the physics front. You'll be here with us, right? Because without you, there's no point in talking about any of this. This is our story. And as always, until we meet again, so glad you're here. With love.